Okay, we will start from a very simple problem, and I will explain how it works, and then we will go with more advanced examples. So the simplest problem we have is we will imagine that there is a supermarket and they want to study which avocado customers would buy. So they collect the data, and they only track two features: the size of avocado and how ripe it is. And they notice that customers prefer bigger avocados and more ripe ones. But they want to build a model. What does a model mean in this case? We will build just a simple line. So we want to find a line that separates negative examples from positive examples. And the way ML usually works is that we start from some randomly initialized values, and then we will do iterative updates until we converge on the right solution. So in the case of like line, we know that a line can be represented as this formula: y equals ax plus b. So our model parameters are essentially a and b here, right? These are the three parameters that define the slope of the line and also the intercept with y-axis. And we also collected a bunch of training data. So let's say ripeness goes from 0 to 1, where 1 is like 100% ripe, it's like a smooshy, and the size also in some units that we decided that are convenient for us. And then the label is whether the avocado was purchased or not. So 0 means it was not purchased and 1 means it's purchased. Okay, so let's say we initialize the model to some random values: a equals 0.4 and b equals 0.3. So now we have this, this is our model, and so what do we do with it, right? How do you train this with this data? How do you perform this training set? First thing I want to do is that, we decided that size is like going along x-axis, and then ripeness goes along y-axis. Which, in algebra, y usually has like more important value than x, so y feels special. It's on a different side of the equation. And I don't want to treat ripeness as more special than size. So we'll do some basic manipulations. We will move y to the right side of the equation. So we're saying ax plus b minus y. And now we see that there is like a parameter a in front of x, but there is nothing in front of y. I don't like that either. Like, why does a have a parameter and y does not have a parameter? Let's add a parameter to y as well. So now we have three parameters. We have ax, by, and the free parameter c. So c is what b used to be before. So I changed also the sign here. It's like it was negative, now it became positive here, because b is a free parameter. We will randomly initialize it, and then as the model trains, it will figure out if it needs to be positive or negative. So it shouldn't matter. And now we have a linear model, but it has three parameters: a, b, and c, which means it's over-parameterized. We know that typically a line can be defined by just two parameters. So since we have three parameters, it means that there are many solutions. Like the same line can be represented by all kinds of combinations of a and b and c. Specifically, I can double all of the values, like double the a, double b, and double c, and still get the same equation, right? This is quite common in ML to have over-parameterized models. This is normal. Sometimes we'll want to deal especially with this, but generally it's fine. Okay, so we have it AX, B, Y, and C, but I just want to rename those. Instead of calling them X and Y, we will call them X1 and X2. Okay, so I'm just renaming X and Y into X1 and X2, which means I have two features, but they don't have like the special names X and Y. It's just like feature 1, feature 2. And same with A and B. I just want to call them like parameter 1 and parameter 2. And usually we call them model weights. So that's why we use letter W. That's what you will commonly see in literature. So essentially this and this is the same equation, which we just renamed a few things. And I'm doing this not to confuse you, but I want to arrive at something that you will see in many other presentations and any other tutorials. So I want to use the similar notation as you would find in other places. Okay, and B is a bias term. So it's very common to call weights that attach to input features as W, and the free weight would be called the bias. Okay, this is like our intercept, like how high above zero, above the origin, the whole line goes. Okay, so let's say we initialized it to some random parameters. And now what? Okay, so now we have this, and we still want to train it. I still didn't show you how to train this model. And since we're going to be training it in code, I want to show you, like, this is a PyTorch Python function essentially that takes two inputs, x1 and x2. Those are floating point numbers, and it also returns a floating point number, and it simply computes this. So x1 plus 0.4 times x, so negative x1, right? This is because we selected -1 as a random initialized value. So this and this should be exactly the same. However, it's not quite the same, because here we say it's all equals to 0, right? We see this equals to 0. Why does it equal to 0? Because initially we had the line equation, right? Y equals ax plus b, and we just renamed a few things, and then we moved the y to the right side, and then we changed this sign, and we added the b parameter. But overall, we are saying that this should be equal to 0, right? But here, when we look at this function, is it guaranteed that this function will always return 0? Not quite. It's actually, you need to work hard to find a combination of x1 and x2 that will return a 0. So what happens when we call this function with various x1 and x2 coordinates? So if I plug in -0.3 and 0, so this one goes into x1, this one goes into x2, we do get a 0. But if we plug in a different value, we don't get zeros, right? So it turns out that when you have a line, coordinates on the line will return a 0, right? But coordinates that are above the line will return a positive number, and coordinates below the line will return negative values. So you only get a 0 when you hit the line exactly. And we will use this property that there are some coordinates above the line and some below the line. Now, what is considered above and what's considered below is a little bit tricky. It depends how we initialize our parameters initially. Because if I flip the sign here, like I can make this positive, this negative, and this negative, then it would still be the same line, but its notion of what's above and below will flip. So But still, for our training purposes, we can say if we plot a line, we want to have, like, we want to call all of this like positive example or negative examples. Those are positive examples, and we will use this notation of like we would want the positive examples to be on one side of the line and negative examples on the other side of the line. Okay, so what is the training process? We will grab a training example. Remember our table here, two coordinates of like x1, x2, and the label 0 or 1. So we will grab this training example, and then we compute. We'll run this compute function, which will return either positive or negative value, and then we want to check that it matches the label. Was it purchased or not purchased? And if the answer is incorrect, then we slightly adjust those model parameters like W1, W2, and P, so that the model will be less incorrect. And we will perform many steps, and eventually it will converge to the optimal state where the line separates the data the best. Now, if you saw earlier in our data table, the labels were 0 or 1, which means 0 we purchased, 1 the item was purchased, and 0 means the item was not purchased. But the way we define this function, we want positive numbers to be above the line and negative numbers to be below the line. So we don't quite have the same labels as what our model returns. Now there are two ways of dealing with it. One way is to change the labels, so like make all zeros to be like negative ones. But instead we will use a sigmoid function. So when we call compute, it will return a value that can be negative or positive, and then we'll plug it into this strangely looking function. It looks scary, but if you plot it, it looks interesting. For all negative numbers, it returns something that's close to 0. For very large positive numbers, it returns something that's very close to 1. And here it has this smooth transition in the middle. Sigmoid is very common. That's why I want to show it at this stage, and we will come back to like when we use sigmoid or something else. So what we will do to compute the loss is that we will first run the compute function, which will return positive or negative value, and then we'll call sigmoid on it, which will convert it into something between 0 and 1, and that will be our prediction. Like our model predicts based on those randomly initialized values whether it's a positive example or negative example. But we also have the real label that says this item was purchased or not, and we check the difference. Okay, the label says this item was purchased, it's the value 1, and then the model predicts that it's a 0, for example. So that will be our loss. Loss means like how far away we are from where we want to be. And so again, what this does is that it says subtract the desired answer from what the model answered and square this. This is a square in Python. So this kind of loss is called mean square error, because we take the difference between what model predicted and what we wanted it to be and squared it. So this is the error, and then we'll want to make the model to be less incorrect, right? So initially, when you initialize the model with random values, this will be very incorrect. And as we start updating the model, it will become less and less incorrect. Okay, so how do we update the model? We use something that is called stochastic gradient descent, SGD. And the way we do it is that for each of our parameters, W1, W2, and B, we want to compute how much each of these parameters contributed to the loss. So like maybe W1 contributed more, made the loss bigger than W2, for example. So the parameter, and there are mathematical ways of figuring this out. And parameters that have a higher effect on the loss, they will get a bigger update in the opposite direction. So we will not update all parameters with the same update. Parameters that contribute more to the loss will be updated with a bigger update. Okay, so how do we know how much each of those contributed to the loss? We use a derivative which you probably studied in calculus if you studied calculus. I don't want to go into details how derivatives work, but luckily PyTorch and other ML frameworks, they actually can do this gradient computation automatically. So you just write your loss function, and then you ask it please compute the loss, compute the gradients, so the derivatives, and it will automatically compute derivatives for you. The only thing that we need to make sure is that all of our compute functions and all of this sigmoid and the loss functions, all of those computations need to be differentiable. What differentiable means? It means that a function is continuous and smooth. So here's an example of not continuous function. I'm saying a function, if x is bigger than 0, then the value is 1, and otherwise 0. So this function goes like this, all 0, for all negative values of x it's 0, and then suddenly it jumps to 1. So this is not a differentiable function. And you wouldn't be able to use that as a loss function, because it cannot be differentiated at 0, because there is this sudden jump. That's why sigmoid is quite similar to it, but it has this smooth transition, right? Here we see the smooth transition. That's why we use sigmoid, because you can differentiate it everywhere. Once you ask your model to your machine learning framework, you ask it, please compute gradients for the loss that I have. Then you apply the updates to your model. So you say W1, this is your model parameter. You subtract the gradient that you computed, multiplied by some learning rate. So it's some small number, 0.01, sometimes it's 0.001. You make a small step in the opposite direction from the gradient, because the gradient says how much this weight contributed to the loss. Gradient itself can be negative. And it means that if you decrease this value, the loss will be higher. But we want to reduce the loss. That's why we're going in the opposite direction of the gradient, right? And we do this for every single weight in our model, every single parameter in our model, with its own gradient. So for each parameter, we compute its own gradient. And so after this update, tiny update, which we make tiny step in that direction, the model will be slightly less incorrect. And then we grab another training example from our table, right? Again, from this table, we will grab the next example, and we'll perform it exactly the same step. And after we make thousands of steps, the model will be much less incorrect. And to help visualize this better, I created this Google Colab. You can open it and you can run it. And there is a Python code that shows how this model would be trained. I hope this was useful. In the next session, we will see how we can make it slightly more sophisticated.